Basically, what transpired prior to the Big Bang, which necessitates caution with the language. Consequently, if you define the Big Bang with extreme caution as the time the universe was extremely dense and hot, likewise, as stated, that cannot be disputed because we can see it from our window. Our preferred explanation for how the universe reached that state is that before that, there was a time referred to as inflation. This question has always been a difficulty for scientists, but now it appears that they have located the solution. It has shocked scientists like Brian Cox, who revealed that a terrifying event existed prior to the Big Bang. So, is the universe the same as it was in a sense of being cold, empty, and expanded extremely quickly? That growth slowed down, came to a halt, and the power that was the expansion's driving force was dumped into space, warmed it up, and produced all the particles from which the universe was made, what we refer to as the Big Bang. Why did it exist before the Big Bang? This frightens scientists. Let's find out. Additionally, that theory has a sort of extension, also known as eternal inflation, which suggests that inflation basically disappears for an interminable time before abruptly coming to patches. So, you can imagine how far the space-time stretch is the universe's fabric. After stretching out, it slows down and comes to a complete stop. In every single one of those patches, there is essentially a massive explosion and a universe that includes our own. So, you end up with a picture like this of a universe of infinite fractals, basically a limitless number of Big Bangs, also known as the inflationary multiverse. The concept of the multiverse in the vast cosmos appears to be absolute nothingness, theoretical as opposed to actual. Even if all energy was taken out of the universe, it would not be truly empty at the moment. Radiation is everywhere in the universe. Nutrients, dark matter, and antimatter. The universe would not exist at all without energy. It continues to produce new forms of energy in this phenomenon that seems to perplex us. The universe doesn't get our idea of total emptiness. If we removed all energy, that leaves a void one would expect the universe to attain absolute nullity with. That is not the case at this time. Its expansion, even in an empty universe, would continue to emit radiation. This extends into the distant past or even further prior to the violent Big Bang. It appears that the universe never truly becomes void. Given everything, is it conceivable that the universe got its start from nothing? But we can guarantee that something persists always, even when particles, quanta, photons, and antiparticles are removed. If we move away from any sources of mass or energy, remove any external electric fields, magnetic fields, and gravitational fields, and prevent gravitational waves or photons from entering a physical form, this area is still devoid of anything. Quantum fields persist, and fundamental rules and constants of physics last, because an inherent zero has a finite, positive, and non-zero value. This is a point of energy in that space, representing the closest possible resemblance to nothingness in our universe. You might picture something even worse, affirming that it lacks physical reality. No experiment can reproduce this kind of condition through scientific principles that we acknowledge, since true nothingness cannot currently coexist in our universe. The reason remains unanswered by science. Currently, our universe appears filled with stars, cosmic rays, gas, dust, galaxies, quasars, and the radiation that comes from starlight and the relics of the Big Bang. With better instruments for observation, we could possibly find additional signals we anticipate will be present. This encompasses waves caused by gravity, produced by any mass that moves through a dynamic gravitational field, cryptic messages from the constituents of dark matter, and an overall view of both active and dormant black holes, other than the ones emitting the most radiation, which is the cause of everything we see in a universe that is both dynamic and perpetually shifting. From a physical perspective, it is fascinating to comprehend the grand scale of our universe's evolution. The known universe's fabric suggests that space-time is expanding. If 2 points are placed far apart in space-time, the distance that separates those two locations and the length of time required for light to travel between them, the wavelength of the light moving from one location to another, all rise over time. The universe is not only expanding but also becoming colder as light expands, moves at longer wavelengths, stretches toward cooler temperatures, and lowers energy. Temperatures that made the universe hotter in the past will further deteriorate into the future. During this process, the universe's mass or energy attracts one another to form groups, establishing an extensive cosmic network. If you were to completely eliminate all content, the entire amount of energy that would be radiated would essentially remain empty. You'd still have space itself continuing to expand, governed by physical laws and still affected by quantum fields. This is the closest to the entire universe's physical similarity to nothingness, yet it continues to follow specific physical laws applicable to a physicist in this particular scenario. Removing any alternative would result in a state that is unrealistic and no longer reflects the universe in which we live. This hints that dark energy, as we currently comprehend it, would nonetheless exist in this fictitious universe. Essentially, meaningless if every quantum field in the universe was set to its lowest state of energy, where we would arrive at the 0-point energy of space. It would be possible to extract more energy for mechanical activity in a universe that includes a cosmological constant or dark energy. The 0-point energy in quantum fields is conceivable that it wouldn't really be zero. As the universe continues to grow and cool, eventually, in the distant future, radiation takes over as the main component, exceeding all other types of matter and radiation, leaving behind dark energy as the primary impact. But there was also a period, not in the future but a long time ago, when something else, in addition to matter and radiation, prevailed during cosmic inflation prior to the Big Bang. The universe changed very quickly with constant growth. Rather than being dominated by radiation and matter, the field had control over the universe's energy of inflation, similar to the current dark energy, but much more effective and expanding significantly more rapidly. Assuming that eternal inflation is true, where might the universe have started? There must have been a first step in addressing this thoroughly. Let's decipher 3 frequently misunderstood concepts and discuss each: the explosive Big Bang, the theory of our universe's relationship to cosmic inflation, and its role in preparing for and preceding the Big Bang, and the question of a final beginning of the universe or its source. Why the original inflation and the Big Bang may not provide a satisfactory response to this query. At the beginning of the 20th century, a significant synthesis was achieved when 4 key pieces of information came together. A breakthrough in the field by Alexander Friedman demonstrated through Einstein's general relativity that a universe uniformly filled with energy and matter in any form cannot remain the same but must either grow or contract. This expansion's rate, or contraction, is influenced by the overall energy density in space. The observational work of Henrietta Leavitt established a relationship between the time period of variable stars' brightness and dimness and their inherent radiance, which is known as the relationship between time and light. Measurements made by Vesto Slipher showed red-shifted or blue-shifted light evolving outside of our solar system's perspective in the elliptical and spiral nebulae that have since been identified as galaxies. The existence of these galaxies was indicated by their rapid movement away from us at high speeds. Alongside Edwin Hubble, Milton Humason identified similar types of variable stars discovered by Henrietta Leavitt in elliptical and spiral forms. This allowed them to measure the nebula in relation to these galaxies and confirmed that they were higher than our own. Together with other data, the findings led to the idea that the universe is growing. If the universe grows, it suggests that space itself expands over time, resulting in... The problem is that as space expands, it contains less dense radiation. Light waves diminish not only in concentration, but also stretch over time. If we rewind the clock, the universe would begin to cool. Conversely, turning the clock the other way around would be relevant. Earlier in the universe, when it was still young, it was hotter and denser. When we rewind further, all radiation and matter would have been constrained to a smaller area, increasing the universe's density. The light that stretched as a result of cosmic expansion would, when time is reversed, result in a shorter wavelength. If you envision higher temperatures extending back as far as physics allows, you'd arrive at a single state where all radiation and matter existed within a single point with infinite density and temperature. The Big Bang's initial concept. The formation of the universe was caused by the Big Bang theory, which has 5 essential predictions for the hot and dense early universe conditions. These predictions underpin the Big Bang theory. First, the universe ought to exhibit expansion due to a distinct redshift relationship between extragalactic objects. Initially, the universe ought to be relatively uniform, with star-like structures, galaxies, and clusters of galaxies gradually taking shape and changing over time. The universe used to be hotter, stifling the growth of stable neutral atoms. As a result of this prediction, the cosmic microwave background was created, which can be observed today. In the very beginning of the universe, when atomic nuclei were extremely hot, they could not solidify, resulting in the creation of light, elements like lithium, hydrogen, and helium. The universe was so hot that isotopes and neutrinos were significant factors. This prediction was recently proven correct, implying that cosmic neutrinos ought to have observable effects on both the large-scale structure and the remaining radiation from the Big Bang. Particularly, evidence from observations supporting these predictions made by the Big Bang theory has remained the undisputed primary explanation for the origins of the universe since the mid-1960s, when the discovery of the cosmic microwave background provided supporting evidence. During the 1960s, the hot Big Bang theory grew, but in the 1970s, a few difficulties emerged that the Big Bang theory alone could not resolve. Some observations went against the notion of the universe originating from a single condition of extremely high density and temperature. 3 obstacles stand out. First, the horizon issue. When we observe different directions, the universe appears to have uniform density and temperature throughout. However, since the blazing fast Big Bang, regions never had the chance to transfer information or attain thermal harmony with one another. This raises the question of how they developed consistent temperatures and conditions. Second, the flatness challenge. In an expanding universe, there is a constant struggle between the forces pushing things apart during the initial expansion and the gravitational forces trying to pull everything back together. These opposing forces in our universe appear to be in perfect harmony, resulting in a flat universe in space. The question becomes, why did our universe emerge with these specific features? Third, the monopole problem. If the universe endured high temperatures and energy conditions in its infancy, why don't we see exotic leftovers like right-handed neutrinos and theoretical magnetic monopoles? These particles should still exist today. In response to these circumstances, scientists used the scientific method to find a system that would organize and explain these initial conditions. Alan Guth provided an answer to these astronomical mysteries. In 1980, he published a groundbreaking paper suggesting that a preliminary period of rapid and ongoing expansion, where the energy of the universe did not spread across matter and particles from radiation, but was a fundamental component of space itself through a field or another mechanism, could solve all 3 concerns: the horizon problem, temperature uniformity, and the overall density of the universe. This interconnectedness deteriorated in the beginning due to inflation, the phase of rapid expansion, resulting in the current state of affairs. Regarding the flatness issue, the universe grew so much due to inflation that, despite its initial state, the visible portion now appears uniformly flat. Concerning the monopole issue, the absence of ancient relics is explained by inflation preventing the universe from reaching energies or temperatures high enough for the emergence of these relics. In the 1980s, accurate inflation theory made predictable predictions about the beginnings of the cosmic structure, observable in the cosmic microwave background and the extensive layout of the universe. These predictions, made decades ago, were confirmed by observations from the 1990s to the present day, encompassing a nearly scale-independent spectrum of imperfections, such as differences in density and temperature anomalies that are completely adiabatic and not isocurvature. These changes occur on scales larger than a signal traveling at the speed of light. The expanding universe may result in a limit on the maximum temperature for the universe, particularly during the hot Big Bang, smaller than the Planck scale. Inflation is the rapid increase of space, rather than reaching a singularity, as in the initial model for the Big Bang. It offers an alternative depiction of the beginning. Space and time gradually emerge from a single state. Inflation suggests an expansion that culminated in the Big Bang. This raises a fundamental question about the actual start of the universe, assuming such a concept even makes sense within the framework of the hot Big Bang. Without inflation, the universe could be traced back to a single state in which its entire size was close to zero in a limited space.